Okay, so I will present use a paper named Energy Aware DNS Server Allocating by Zheng Wang and Scott Rose, written in 2018. So before all, my work. So my subject of PhD is the analysis of the environmental impact of DNS. In other words, it's to propose a mathematical model and a methodology to measure the energy consumption of the DNS. DNS is a domain name system for a potential application in the life cycle assessment, which is um, it's a protocol to establish an environmental footprint of a service, a company, or a product. So the measures that I will have with my thesis uh, have an application in that. And so now my current work is about studying paper on DNS modeling. And so this paper proposed a mathematical model to reduce DNS energy consumption, but without impacted quality of service. So first, the DNS. Hop. Tac. So the domain name system, for somebody who don't know what is a protocol which translates an URL in human language, for example, docs.toto.bzh, to another CP for machine language. And how it works, so a user sends a request, doc.toto.bzh, and the DNS resolver server is the server in the DNS system, which is a node between all the name servers. So the name server are root, TLD, and authoritative servers. And when we send a request to the resolver requests the root server to know where is the TLD server of the .bzh or .fr or .com, etc. Dot. After the resolver sends the request to the TLD server, which know where is the authoritative server, where all the sorry, where are registered the the IP of the web server. So in this paper, the objective is to reduce the energy consumption of the name server without impacting the quality of service by approaching the problem through analytical model. And a little, I will introduce the lot of variables. There is very lot of variables with a beautiful diagram. So in this paper, they say that we have G resolvers, big G resolvers, and we have N name server. So name server are root, TLD, and authoritative server. And in each name server, we consider that a name server is like a data center of big ME machines. And in these big ME machines, we have only ME machines turn on. And this resolver sends a lot of requests. So we have BQGs, the average rate of requests sent to all name server by the resolver number G. Just the average rate of requests sent by resolver G to name server E is named lambda EG of T. And the total of lambda EG, which arrived in the name server E, is called lambda E of T. Okay, and in that big configuration, we have the energy consumption. They let GE, okay, yes, G, the energy consumption of name server E, and lambda E is the energy consumption depending of T. In the paper is approximately the same thing. We have the revenue loss due to a delay D, so the time that a request go to the name server and go again to the resolver is named D. And we have the service rate of name server E of each machine in the resolver E, which is the number of requests each machine can process per unit per unit of time T. The total delay. Okay. Sorry. We have yes, we have F, which is the delay due to the queuing, because when there is a lot of requests, the request create a queue in each machine. So we have LEG, the total delay of a request from reservoir G to name server E, which is addition of FE and DE. And the total delay cost of name server E is expressed by the sum of all lambda E, G, okay, multiplying by the revenue loss. And the two last variable, we have gamma G, which is the load distribution of requests from resolver G across different name server, and L, the delay distribution between resolver G and different name server. Okay, there is a lot of variable, but it's good. Tac. Okay, sorry. I can access, yes. Okay. To help you, yes, okay. So the goal is to minimize the sum of lambda E, which is the energy consumption, and sigma E, which is the delay of a request, but with the constraint that ME can't be null, because if small ME is null, it's like there is no machine activate. So we can just stop the DNS and yeah. And ME can't exceed the maximum. And ME is and integer because we can't cut a machine into parts. Tac, tac, tac. And they develop this formula before optimize it, yes, optimize it. The first hypothesis is that they consider there is just an interval and they omit the time dependence. So it's the same thing, but with no time dependence. The second hypothesis is that the revenue loss is linear. So the revenue loss could be expressed at like a constant multiplied by the delay. And they have an hypothesis about queuing-based delay, assuming by that workload is parallelized, and Fe represents the average delay of ME parallel Q. Then they express Fe as 1 on mu e minus lambda e on ME. So the denominator represents the number of requests of a machine at name server E can process minus the actual incoming request per machine. And they say that GE is PE, so the energy cost of an N for one machine multiplied by the number of machines active. So they express the problem as a big formula called SIQ, and this formula is optimized in the next of the paper. Yeah. So in the formula we find P multiplied by ME. So it's the energy consumption plus the delay, the cost of the delay. Tac, tac, tac. So next, they optimized this formula. So to do that, they say that SAQ is convex and satisfies Slater's condition, so the Karush-Tucker conditions are necessary and sufficient for optimally, and they can develop the Lagrangian with the introduction of Lagrange multipliers, omega underline E, omega overline E, and gamma E. So in the Lagrangian, we find yes, we have the formula to optimize, and the conditions like that with the Lagrange multipliers, multiplying by Lagrange multipliers. Sorry, and according to KKT conditions, we have first the stationary. So the gradient of the Lagrange is 0. So they derived the Lagrangian by ME because we search the optimal value of ME, the number of machines we need to activate. Sorry. And okay, so they have a formula. And according to KKT conditions, we have complementarity slackness, primal feasibility, and dual feasibility that can express like these three formulas equation. Okay. Tac, tac, tac. And to align the equation, they define that P star is equal to P plus the three multiplier, enfin, plus, less, well, plus, less, minus, and minus. And with the development, they find the optimal solution given by ME with a wide hat equal to 1 plus square t of beta and pi star and multiplied by lambda e and mu e. For a valid solution, we must ensure that this optimal solution is less or equal to the maximum number of matching. Yeah, and they give three theorems. First, they say that ME is never zero because, like I say, if ME is zero, we can just stop the name server and it's finished. Yeah.
So if we stop one name server, there are the other something, right? Or did I understand?
No, if we stop all the servers on the name server, we can just kill the name server.
Exactly. But there are the other name servers.
Yes, there are other, but the delay increase. Yeah, and they say that ME doesn't equal to big ME because if we activate all the server, the energy cost is really big and it's not the goal of the project. We can if we need to have
so it's the same as like just defining differently the budget, no? Instead of MI, they say it's MI. So I don't understand. If you have all the servers, just you can use them.
yeah, no, they say that we don't which MI because MI is surdimensionné to for the peak of number of requests. So in the reality, MI doesn't reach big MI. So they say that the constraint is said to be inactive. It's a optimization theory. So they can say that multipliers are zero in these conditions, and they can simplify the optimal the formula of the optimal point, and at the optimal point, the average delay of the MA Barré is FE equal to that. It's just development from the formula before with MI with the new formula of MI. So they say that a unique optimal solution exists if MI is less or equal to big MI is always satisfied. tac, tac, tac. So if all the Lagrangian multipliers are 0, pi star begin pi. And so they simplify the formula of optimal of fi. Yeah.
Just compare the formula for the two. No, can you show? No, it will be too big. No, what I want to compare is the formula in theorem 1 and theorem 2. Just, no,
Okay.
but I need
it
to see
just,
the both. No, the formula of mi. It seems the same, no?
Yeah, it's the same.
No, so you here you have theorem 1. No, not this formula, the formula within the theorem 1. Theorem 1, you have mi
Yeah.
equal to this formula. And can you go, isn't it the same formula for theorem 2?
It's the same. It's just a condition.
Okay.
It's,
So nothing changed in that case?
no,
I don't understand.
they say that if we have this formula, so FE, the optimal FE is that,
Yeah.
and could be
Yeah.
simplified as that.
Okay, but then so no, just we obtain the delay. Okay, but in theorem 2, so I do not understand the difference between the two theorems for the moment.
It's just observations. So in the first, they say that we have a unique solution. It's a consequence of that.
Okay.
And
But I need to understand.
and with that, they say that the average query processing delay, so F, is independent of the incoming query rate lambda E, because we have.
So it's with the same condition as theorem 1, in fact.
Yes.
Okay.
Yes, always. And the third theorem with the same condition. Tac, tac, tac. So they let GJ denote the server selection function. Tac, tac, tac. So we have the loud distribution, and they say that the server selection function depend on the delay distribution between resolver to name server. And tac, tac, tac. And LE, so all delay can be expressed like the formula, the same that we see before. And according to the theorem 2, so tac, 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 they just develop LE of G with the formula of optimal FE. And they say that in the context of optimal server allocation, the average query traffic from resolver G to name server E is constant. Okay, sorry. I don't know what I say. Yes. Yeah, the average query traffic is constant for the optimal server allocation. There is many effects. So if we take the formula of optimal FE, we can see that if we fix the PI, so the energy consumption, the FE, so the query processing delay, decrease if the processing capacity increase. So the resolver prefers to select a name server with the highest UE, with the highest processing capacity because it's faster. And so increasing UE while keeping PI constant is always effective for reducing energy consumption. And the second thing that they say is when we fixed UE, so the processing capacity, FE decrease with PI decrease. So the resolver prefer name server with better processing delay FE, and it's correspond to lower energy consumption PI. And in that case, there are reducing energy consumption. Yeah.
Increasing mu, increasing mu I,
Yeah.
does it have an impact on the energy consumption or not? So we can, because I would assume if increase
yeah.
processing capacity, you also increase the energy consumption. So saying I increase capacity, but the energy remains the same is a bit idealistic. I would guess. I don't know.
Could you repeat, please?
So mu I is
Yeah.
the processing capacity. So you say that increasing, they say increasing mu I while keeping PI constant is always effective. But it seems like a dream, no? That you can increase mu I while keeping the energy the same. So you increase the capacity by keeping the energy the same. Yeah, that would be nice. But
Yeah.
I don't know if they discuss this thing or it's a misunderstanding from my side.
I don't know in the reality if it's when they say that it's theoric, and they think that with this formula, how express? Yeah, no, I don't.
It may just be a mathematical.
Yeah,
it may
yeah,
just
it's
be a
just mathematical.
observation. Like in the formula, yes, of course, increasing mu I while keeping PI constant. It's the mathematical fact. It's not like you can do that.
Yeah.
This I don't need any mathematical development to say that if I make something more computationally powerful without increasing energy, everybody's happy. So I reduce energy. I mean, this is too trivial to be obtained via equations, right?
Yeah, in the problem, they say that they want to have a better consumption, but with not loss of
Delay.
delay. So they say that even we have a PI constant, the delay is better. I don't know how to explain.
Another question.
Yeah, I think the second affirmation is more realistic, more in their problem. Yeah.
So they made this assumption, and I think we went very quickly through them. So they make this assumption. So the cost is independent on the load that you have in this time chunk, because this is how the problem has been set, and so this is how it has been solved.
Okay. Okay, but in the reality, the cost and the delay are dynamic and depend of the time. So to simplify their problems, I decide to decouple the machine allocation problem at name server and the server selections problem at name server. So they say that the machine allocation problem at name server is choose recursively based on the lambda e, pi e, and tag during the time before. And there is this function, and so it's just the result of the previous time to choose to choose the allocation the allocation machine on t plus one. And the server selection problem, it's the same. So they say that they choose their problem based on each delay for request in the time before.
Sorry, just a quick point with respect to what we were saying before about the power consumption. So apparently in their simulation, they are assuming different energy costs for kilowatt hours in different name servers in different cities, including different distances for reaching actually the between the resolver and the name server. So this means that if you go to one resolver situated in this city, you pay some electricity bill because you are consuming that amount of energy. So that thing is possible in the sense that the capacity may stay the same just because you choose another place where the energy cost is less. I think it's still a little bit unrealistic. Yeah, it's also unrealistic because they assume that the delay increases linearly with the distance, which may not be necessarily true. But anyway, I think this replies to the question: how can this be possible? It may be if you have different consumption in different places.
They talk about that after. They talk about, just in 5 minutes. Ah no, it's not. Okay. Ok. So yes. Tac, tac, tac. Ça sera mieux comme ça. So they decide to test the performance of their model, and they consider that we have G equal to 10,000 resolvers. The average of query of each resolver sent to Olean server is equal to 300. There are 6 name server in 6 cities in USA. So California, Washington, Illinois, Texas, Florida, and Virginia. And each state has their own cost of the energy. So, for example, California, a kilowatt hour of energy costs 10.41 cents of dollars. Okay, so they have in each name server approximately 1,800 machines, and each machines have a mu of 18 QPS. So they could query per second. They could result 800 query per second. They fix beta, so the constant of the revenue as 0.005. I don't know why, but they fix that. And they say that D, so delay of the trajectory of the queries is increased by 1 millisecond every 100 kilometers. And they say that there is a big limit. It's that the unit of energy cost is the dollars, and the unit of the delay cost is the second. So maybe in a second time, it will be better to find a cost equal with the same unit, because now the values are only relative. So yeah.
It's the beta that does this conversion implicitly, I think. This 0.005, I think
Yeah.
it's dollar per unit of delay.
Yeah.
I think so. Yeah.
Yeah, it's just an adjustment, and maybe if we need to have a better delay, we can adjust beta, but it's really relative. Tac. So first, they test an uniform name server selection, and after in RTT-based name server selection. So why uniform name server selection? It's because a lot of DNS resolver, actually, for example, Unbound, Windows DNS, etc., have a selection which is uniformly distributed by conception. So they evaluate the performance comparing the performance of the theoretical proposed energy aware server allocation by comparing two cases. So all on when all machine in a name server are used, and often when only the half of the machine are active. And they have they have two graphs. Well, there are other graphs, but these both are really representative of the next of the paper. The optimum result is lower in the both of case. The loss revenue of the optimum is less. In the first case, it's because the energy consumption increased faster than the delay cost decrease. Because in this case, the all-on configuration have a better delay cost, but a worse energy consumption. And when they addition the both, they see that the loss of revenue of optimal is less than the all-on lost revenue. And in the second case, we see that the alpha lost revenue tends towards the optimum. But when we have a little big M, the delay cost explodes, and so the loss of revenue explodes with that. Yeah. Tac. And after they, to validate their iterative method, they decided to implement a server selection algorithm based on RTT. RTT is one type. So it's the time of okay. When we send a request to have the response, we have a time on its RTT. So they implement this algorithm in a bind resolver. Bind is really popular in DNS and could be applied on a lot of servers. And each RTT retrieves from the set of 6 name server, determines the proportion of lambda EG, so the average weight of queries for each resolver, depend of the precedent iteration. And they have a first result. So they see that the system quickly converge to the optimal point, and it takes approximately 8 iteration to reach the convergence. Yeah. In this case, they the first at the first time they distribute the lambda EG totally randomly. In another case, they decide to distribute that equally. But yeah, it's better to see that. Yeah, and they say that in real DNS environment, there is sometimes a disruption in the traffic distribution, and they decide to test the robustness of the iterative method against this disturbance with the introduction of disturbance during when traffic distribution is stable, and the result is that so they reach the convergence, and after the disruption, the query traffic reach the second convergence, so the convergence again after 8 iterations again. So yeah, it's a result of their model. Well, I don't know if you have some question.
So I have one question about their approach, because in their, I did the simple control F. They did not mention any caching, any possibility that the resolver has already the response inside, right? It could be interesting to understand what is the impact of this, because in this case, the resolver has already the mapping internally. It does not need to go to the name server.
Yeah, the cache is the cache processing is in the resolver. So all of that is after this step of have I the cache in my system? We yeah. Yeah, no, the caching is another part all the equation, and between resolver and name server, we don't have cache.
Yes. And in fact, this is the reason why I'm asking this question, because if the resolvers are aware that there are caches, independently from the number of queries that they receive or that they can measure or that they can predict, they can decide actively to stop instead of being always active. So I mean, it's over-dimensioned, as we said before, but they can also they can do even less than what they do right now.
Yeah, maybe, but yeah.
So this is a general question. It's not a question about this paper. My question is, DNS works by massively caching queries in our resolvers. But DNS servers are always in active state because they must be able to respond to any kind of question. So if the name servers are aware that resolvers have the possibility of caching, and instead of having a pull approach, so the resolver asks, yeah, it's after caching, it's the request right after caching. But what I mean is that this assumption is like, okay, the resolver has this request rate, but this request rate can be arbitrarily low. It can be minimized a lot. In the sense that if, so suppose that all the resolvers have caches and they always hit. So they hit.
Have timeouts?
Yeah, exactly. I know. So this means we're playing on the timeout.
Yeah, so with assumption they do lambda bridge.
Your case would translate to having low lambdas, but the model would remain the same. So it's a low lambda because most of the queries are response by cache.
Yes, exactly.
But the model should be valid anyways.
Yeah, just Q is a result of the query with not satisfied by the cache.
Okay.
Yeah.
So something that is not really clear for me is the quality of service. I don't know how to define this because so it will be maybe related so directly on this paper or not about energy consumption. Let's suppose we have a lying DNS resolver. And for me, the quality of service is not related to the DNS request, but it's related to the service that I will access thanks to the DNS. So for example, I have a web page which contains a lot of advertisements, and I don't want advertisements. So I use a lying DNS resolver that block ads domain names. So for example, by sending back loopback IP address instead of the real advertisement domain name when the request is sent to the lying DNS server. So I will have a better quality of service, but I don't know if it is this good definition, and I will probably reduce my energy consumptions because I don't have to send another request from the resolver to the other name servers.
Okay, so in this paper, the quality of service is the time of response. So
Okay.
if we have a big time of response, there is no quality, no quality in the DNS.
Okay.
So no, it's not that.
And so do you plan, maybe it's not related to that, do you plan to study this kind of aspects that are not related to the DNS itself, but to the global system that involve DNS?
Maybe later, but it's not
Okay.
in my line of view now.
And another question is, so the protocols that are used is raw DNS. Do you study also DOH or DOT or DO quick?
Yes, I think it's here it's just DNS over UDP.
Yeah.
Because between a resolver and name server, it's UDP. But yeah, I will study the modelization of DOH and DOT. I know what is it, but I don't study paper about modeling of that.
Okay.
But yeah, DOH and DOT have, I think, there are a great impact on the energy consumption because we have all of the layers of security, of cryptography, etc. Yeah.
Okay.
It's
Thank you.